Welcome, cosmic explorers, to a mind-bending journey into the wildest corners of the universe. Today, we're diving deep into the fascinating realm of neutron stars and pulsars, the universe's densest objects, where gravity, physics, and sheer cosmic power push reality to its limits. Imagine a star so dense that a single teaspoon of its material weighs billions of tons, spinning at blinding speeds and beaming energy across the galaxy. How do these bizarre stellar remnants form? What makes them tick? And why do they hold secrets to the universe's deepest mysteries? Buckle up, because we're about to embark on an epic adventure that will stretch your imagination and leave you burning with curiosity. Let's unravel the story of neutron stars and pulsars together. Picture the night sky, a vast canvas of twinkling stars, each a fiery furnace living out its life. But some stars, the massive ones, don't fade quietly. When they die, they leave behind extraordinary remnants, and among the strangest are neutron stars. These are the crushed cores of massive stars, packing incredible mass into a sphere just 10 to 20 kilometers across, smaller than a city. Their density defies comprehension, and some of them, called pulsars, spin wildly, firing beams of radiation like cosmic lighthouses. These objects aren't just oddities, they're keys to understanding gravity, matter, and the universe's violent past. Doesn't that make you wonder what kind of power creates such extreme wonders? Let's start with the birth of a neutron star, a story tied to the dramatic end of massive stars. Stars begin in clouds of gas and dust, collapsing under gravity to ignite fusion, turning hydrogen into helium and heavier elements. For stars 8 to 20 times the mass of our Sun, this life burns bright but fast, lasting just millions of years. They fuse hydrogen, then helium into carbon and oxygen, and onward to silicon and iron in a layered core. But iron is the end of the line, fusing it consumes energy, not releases it. When the iron core grows to about 1.4 solar masses, a critical limit called the Chandrasekhar limit, it can't hold against gravity. In a fraction of a second, the core collapses, and the star's fate is sealed. What happens next is explosive. This collapse is catastrophic. The core, once Earth-sized, implodes to a ball 10 to 20 kilometers wide. Protons and electrons get crushed together, merging into neutrons and releasing a flood of ghostly particles called neutrinos. These neutrinos blast outward, carrying away energy, while the outer layers of the star crash in, then rebound in a colossal explosion, a supernova. This dazzling blast, visible across billions of light-years, outshines entire galaxies for days. Supernova 1987A, observed in 1987, gave us a front-row seat, with neutrinos detected confirming the theory. The core, now a super-dense ball of mostly neutrons, becomes a neutron star. Isn't it wild to think a star's death births such a dense marvel? Now, let's explore the neutron star itself. Imagine squeezing 1 to 3 solar masses, hundreds of thousands of Earths, into a sphere the size of a small city. A teaspoon of this stuff weighs as much as a mountain, around 1 billion tons. This density comes from gravity crushing matter to the edge of physics. The core is mostly neutrons, packed so tight they're nearly touching, held by the strong nuclear force, the glue of atomic nuclei. The surface, a thin crust, blends neutrons, protons, and bizarre nuclei, maybe even a pasta phase, strange shapes like sheets or rods from extreme pressure. Above, a faint atmosphere, mere meters thick, glows with heat. This is matter at its most extreme. Can you fathom such a compact powerhouse? The structure of a neutron star is a cosmic puzzle. The outer crust, a kilometer thick, is a lattice of nuclei and free electrons, rigid but cracking under strain. Deeper, the inner crust mixes neutrons in a superfluid, flowing without friction, a quantum weirdness. The core, shrouded in mystery, might be a sea of neutrons, or perhaps exotic particles like quarks, freed from normal matter, or even hyperons, strange cousins of protons. Some theories hint at a state called quark-gluon plasma, a soup from the early universe. We don't know exactly, because no lab can mimic this density, billions of times denser than Earth's heaviest materials. The mystery fuels our curiosity, doesn't it? What about gravity? Neutron stars test Einstein's general relativity to the max. Their gravity warps spacetime, bending light and time itself. A clock on the surface ticks slower than one far away, a relativistic trick called time dilation. Their mass, packed so tight, stops short of a black hole, balanced by neutron pressure, called degeneracy pressure, resisting collapse. If the core exceeds 2 to 3 solar masses, even this fails, and a black hole forms. The Tolman-Oppenheimer-Fokoff limit, a theoretical cap, hints at this edge, but exact numbers elude us. These stars are labs for extreme physics, bending our understanding. How wild is that? Now, enter pulsars, the spinning wonders of the neutron star family. When a massive star collapses, it spins faster, like a skater pulling in their arms, a law called conservation of angular momentum. Some neutron stars whirl hundreds of times a second. Strong magnetic fields, billions or trillions of times Earth's, channel charged particles into beams from the poles. If the star spins and these beams sweep past Earth, we see pulses of light, radio waves, X-rays, even visible light, like a lighthouse. In 1967, Jocelyn Bell Burnell, a graduate student, spotted the first, a steady tick every 1.33 seconds, dubbed a pulsar. Her discovery stunned the world. Doesn't that pulse quicken your own? Pulsars are cosmic clocks, incredibly precise. The first, PSRB 1919+21, pulsed reliably, sparking wild ideas, alien signals, before we knew they were stars. Some, like the Crab pulsar, born in the Crab Nebula from a 1054 AD supernova, spin 30 times a second, powering the nebula's glow with energy. Millisecond pulsars, spinning hundreds of times a second, get sped up by stealing matter from a companion star in a binary system, a process called accretion. Their precision rivals atomic clocks, letting us test gravity, detect gravitational waves, and map the galaxy. Imagine a star ticking like a cosmic metronome. Let's dive into magnetism, because neutron star fields are unreal. Born from the dying star's field, amplified by collapse, they range from 100 million to a quadrillion times Earth's. In some, called magnetars, fields hit extreme highs, twisting matter and space. These fields whip particles into jets, powering pulsar beams in radio, X-ray, and gamma-ray light. Magnetars quake, too, with starquakes in the crust releasing bursts of energy, flaring brighter than the sun in seconds. The magnetar SGR 1806-20, in 2004, unleashed a gamma-ray burst felt across 50,000 light-years, jolting Earth's atmosphere. What kind of power drives these outbursts? How do we study these beasts? Telescopes are key. Radio dishes, like the Arecibo and Green Bank, catch pulsar pulses. X-ray telescopes, like Chandra and XMM Newton, probe hot surfaces and jets. Neutrino detectors snag hints from supernova births. In 2017, LIGO and Virgo detected gravitational waves, space-time ripples, from two neutron stars merging, a collision that glowed in light and forged gold, silver, and heavy elements. Computer models simulate cores, testing exotic matter. Each tool peels back the mystery, revealing density, spin, and more. What new windows will open? Neutron stars shine in binary systems, too. Often, a neutron star pairs with a normal star, pulling gas via gravity. This matter spirals in, forming an accretion disk, heating to millions of degrees, and glowing in X-rays. Systems like X-ray binaries pulse with energy, some spinning the neutron star into a millisecond pulsar. When two neutron stars orbit, they spiral closer, emitting gravitational waves, and merge in a kilonova, a blast of light and elements. The 2017 merger, GW170817, confirmed this, linking waves to gold in your ring. These pairs dazzle us, don't they? Let's explore their cosmic role. Neutron stars tie to supernovae, scattering elements, iron, gold, uranium, forged in their births or mergers. These seed nebulae, birthing new stars and planets. Your body's atoms, from ancient stars, connect you to this cycle. Pulsars map the galaxy, their pulses tracing distances and magnetic fields. They test relativity, 2 PSR 1913 plus 16, a binary pulsar, loses energy to gravitational waves, matching Einstein's predictions, earning a 1993 Nobel. Neutron stars shape the cosmos, past and present. How do you fit into this story? Challenges abound. Density defies labs, we can't crush matter that tight. Core physics, maybe quarks or hyperons, eludes us. Pulsar beams puzzle us, how do they form? Mergers are rare, hard to catch. Yet, scientists innovate, blending radio, X-ray, and wave data. Telescopes like the Square Kilometre Array, coming soon, will hunt thousands of pulsars. Models push boundaries, probing exotic matter. The universe tests us, sparking brilliance. What hurdle will we leap next? Let's bust myths. Neutron stars aren't black holes, gravity's strong, but light escapes. Not all are pulsars, only some beam our way. They're not alive, just dense relics, glowing from heat and spin. And no, they don't destroy the galaxy, they build it, seeding elements. The real tale, collapse, density, pulses, outshines fiction, blending physics and wonder. What surprises you most? The future excites us. The James Webb Space Telescope peers at supernova remnants, hinting at births. The Square Kilometre Array will map pulsars, testing gravity. LIGO and successors hunt mergers, tracing waves and elements. We'll probe cores, decode magnetism, and watch collisions live. Could a nearby pulsar tick? might emerge or light the sky. The quest unfolds, full of promise. What does this mean for us? Neutron stars and pulsars, densest of all, reveal the universe's extremes. They forge your atoms, time the cosmos, and bend space-time. From ancient stargazers to modern detectors, we chase their story, driven by curiosity. You're stardust, tied to these wonders. This journey, from collapse to pulse, lights our path. As we near the end, let's gaze ahead. Neutron stars and pulsars dazzle, hiding secrets of density, spin, and gravity. New tools, waves, and light will unravel them. What lies in their cores? How will they reshape physics? The cosmos beckons, full of wonder. What questions stir your mind? Thank you for joining me on this epic dive into neutron stars and pulsars, the universe's densest objects. I hope your curiosity blazes. If you loved this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about neutron stars? What mysteries should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Explorers.